NOAA's Science on a Sphere. This is a creation of the Earth System Research Laboratory, Boulder, Colorado.
Most major hurricanes, go through that rapid intensification, and that's the area where we need help. Fortunately, that happened with Rita out away from land. If that had happened when it was passing through the Florida Keys, it would have been catastrophic down there. We've identified that as the #1 area to the research community as the area where we need the most help in.
You're looking at a system developed by NOAA called Science on a Sphere. Science on a Sphere is a display system designed to make Earth and other planetary sciences more accessible and understandable to the public, particularly to school students. Global environmental data can be better understood when it's converted to images and then shown on Earth's native format. On a sphere, visualizations of environmental processes and relationships provide an appreciation of the connections between the oceans, atmosphere, and land. Science on a Sphere has no moving parts, but instead uses computers to project animated images onto the surface of a large sphere. Now let's get started on a short series of scientific visualizations.
You are now looking at a computer-generated picture of the Earth's topography and bathymetry developed by NOAA. The computer uses color to distinguish features on the planet. On the land, the color gray and red represent the highest mountains, with yellow and green being the lowest points on the land. In the ocean, the light blue colors represent shallow ocean and continental shelves, while the very dark blue represents deep oceanic trenches, miles below the sea surface. It is well known that the land of the Earth contains many mountains and valleys, but what is less well known is that there is a tremendous amount of terrain under the ocean. The Mid-Atlantic Ridge is a striking feature that splits the Atlantic Ocean down the middle and is in fact the planet's longest mountain range. Liquid hot magma is constantly being pushed up from the planet's core along the Mid-Atlantic Ridge, creating the mountains and seafloor. This perpetual yet slow process is making the Atlantic Ocean wider at a rate of 2 inches per year, and at the same time pushing the American continents further apart from Europe and Africa. Also, notice the dark blue indicating deep trenches in the Atlantic and Pacific Oceans. The Marianas Trench, located in the West Pacific near Japan, is nearly 6 miles deep and is the deepest part of our planet. There are many such features to be found in the ocean and appear on this visualization as fracture zones, or things that look like scratches on the ocean floors. Many of these visible features are the results of tremendous and ongoing plate tectonic forces that have shaped our planet over billions of years.
Now please walk slowly to the other side of the sphere for something completely different.
Here, on the dark side of the Earth, are the lights of the Earth at night. This data comes from a network of polar orbiting satellites in the Defense Meteorological Satellite Program. These satellites circle the planet at tremendous speeds between 8 to 15,000 miles per hour. The satellites take pictures constantly as they pass over the Earth, and scientists and computers process this collected data. There are 3 kinds of lights shown here, which represent 1 year's worth of data collection. The white lights are generated by electric sources. The yellow lights are from fires, and the green lights are from fishing fleets. The fires in Africa are caused by burning the fields and grasslands to replenish the nutrients in the soil for growing crops. In the United States, you can see how the lights show the paths of the interstate highway system. We have developed so heavily along these highways over the last 30 years that they are now visible from outer space. Also note the heavily populated areas along the coasts in Europe and elsewhere around the world.
Next, we'll look at a couple of conditions which are necessary for the formation of strong hurricanes. This black rectangle here is the hurricane genesis region. One thing hurricane forecasters look for is a lack of vertical shear. In other words, not much change in the wind from the surface up to higher in the atmosphere, say 30,000 feet or so.
This animation shows infrared satellite cloud images from a network of geostationary environmental satellites. The data presented here covers late July through September 2004, when 4 major hurricanes struck Florida. This information was used for observing and tracking the hurricanes. Around August 9, 2004, a tropical storm starts forming just north of South America. It moves quickly across Cuba and becomes a tight hurricane. This is Hurricane Charlie, and it moves through Florida, striking on the state's west coast, and then moves across in an unusual eastward track. Next, you see another hurricane forming in the Atlantic and moving northward up the middle of the ocean. This is Hurricane Danielle, which did not hit land. After a break of a few days, a major storm starts forming off the coast of Africa. Tropical Storm Francis quickly becomes a powerful hurricane and heads straight across the Atlantic and crashes ashore in the Bahamas. Francis loses some energy there, but then moves across the open water to slam into Florida's east coast. It spins up the state and drops a lot of rain on the southeast. The storm skimming the top of South America is the season's strongest storm. This is Hurricane Ivan, a Category 5 storm. Ivan hits Jamaica, doing a fair amount of damage, and then shoots the gap between Cuba and the Yucatan Peninsula. It flounders a bit, and then comes ashore near Mobile, Alabama and the Florida Panhandle area as a Category 3 hurricane. Now for 2 hurricanes at once. Hurricane Jean off the coast of Florida was the 4th hurricane of the season to hit Florida, while Hurricane Carl in the middle of the Atlantic decides to head north following Hurricane Danielle, sparing Florida a 3rd punch to its east coast. One more interesting feature of this data set is the intermittent line of storms circling the equator all around the world. This area is called the Intertropical Convergence Zone. Some of the storms that impact North America originate in this zone. This next data set helps illustrate the phenomena known as El Nino and La Nina by showing 20 years of sea surface temperature differences starting in the year 1980. The temperature anomalies, which are the differences from historical average temperatures, are provided by NOAA's National Climatic Data Center in Asheville, North Carolina. On the sphere, please find that part of the Pacific Ocean next to the coast of South America, which is where El Nino and La Nina events occur. The color scheme is pretty easy to follow. Green indicates normal sea surface temperatures. Blue and very dark blue indicate cooler temperatures. And yellow, orange, and red reflect warmer to much warmer water temperatures. Now, let's start the sequence. Looking at the Pacific Ocean, you're going to see an ocean event that periodically occurs off the coast of South America. That event is called El Nino. It can have a dramatic effect on the weather of North America, especially the west coast. At the end of 1982 into 1983, there is a significant El Nino event extending thousands of miles out into the Pacific Ocean. Note the significant warming of the sea surface along the coast of Baja California. The changes in the surface temperature of the ocean affect the path of storms. The storms move lower down the coast, churn up the sea surface water, and suppress the normally very cold California current. The opposite of El Nino is the La Nina. The La Nina occurs in the same area of the Pacific, but instead of warm surface water, La Nina is characterized by very cold water at the surface, represented by blue and purple colors on the sphere. Although La Nina has a pronounced effect on the weather and climate of South America, its effect on North America is rather minimal when compared to El Nino. Now, get ready for the strongest El Nino on record, the 1997-98 event. Two major weather events in North America are attributed to this El Nino: a 5-day ice storm in the northeastern U.S. and southeastern Canada, causing widespread power outages, and also severe rainfall flooding in Southern California, causing enormous property damage and some deaths. Our increasing knowledge of El Niños will help with predictions of such severe weather events in the future.
Max, Mr. Hurricane, I turn it over to you. Thank you.
I want you to stand. We'll talk about Wilma. Wilma's coming up here in a few days. This loop stops at the end of October. This is what eventually becomes Wilma. Wilma actually right there on the 18th and 19th went from a tropical storm to a Category 5 hurricane. We've never ever had that rapid intensification before. Luckily that occurred over the open waters of the Caribbean and not near land.
NOAA's Geophysical and Fluid Dynamics Laboratory in Princeton, New Jersey, developed this climate change model, which predicts the mean surface temperature of the Earth over the next 500 years. Carbon dioxide, a greenhouse gas, has increased 35% during the past 200 years and continues to increase in the atmosphere. This model assumes that the amount of carbon dioxide in the atmosphere will increase at the rate of 1% per year, every year, for the next 140 years. This quadruples the amount of carbon dioxide in the air over what it is today. After 140 years, the amount of carbon dioxide input stays the same year after year. At the beginning of the model, the green color coding reflects an average surface temperature. Blue means the temperature is a little cooler than normal, and the yellow and orange are a little warmer. As the animation starts, notice the light red color starting to appear. Light red indicates a surface temperature of about 5 to 10 degrees Fahrenheit warmer than in the year 2000. Dark red means 10 to 20 degrees warmer, and black indicates an area up to 30 degrees warmer. At about 100 years out, the polar ice caps have completely melted. Notice that the northern hemisphere heats up more than the southern hemisphere. Why? There is more water in the southern hemisphere than in the northern hemisphere relative to the amount of land. Water is a great moderator of temperature changes and heats up more slowly than the land. This simulation assumes that low and mid-level clouds will burn off, allowing a lot more surface warming. However, the role of clouds in global warming is still unclear today. Notice that after 140 years, even though the carbon dioxide levels stop increasing, the surface temperatures do not cool off. That's because carbon dioxide persists a long time in the atmosphere, and reversing the effects of global warming, if possible, may take centuries. Now, let's take a look at an X-ray image of our Sun, which allows us to see its outer atmosphere, called the corona. The corona is where the solar storms are occurring, those white flashes you see periodically. This dataset is derived from a sensor located on the NOAA GOES weather satellite. The Space Environment Center in Boulder, Colorado, uses such images transmitted every minute to predict the weather in space caused by the Sun. Solar storms, such as flares, solar eruptions, and coronal holes, can cause interruptions to our satellite communications, navigation equipment, power line transmissions, and space travel. It takes only 8 minutes for a surge of increased radiation to reach the Earth from a solar storm. Like the Earth, the Sun also rotates, on average every 28 days. That's an average, because the Sun rotates faster at its equator than at its poles. And that's possible because the sun is a big sphere of hot gases and nuclear reactions, constantly changing. If this were the actual size of the sun, how big would the Earth be in comparison? Well, the Earth would be about the size of a nickel. Before leaving this image of the sun, you should know that this data set is actually a duplication of the same sun image on the two sides of the sphere, as there are no satellites on the opposite side of the sun to take its picture.
My name is Russ Green. I've been with the Thunder Bay National Marine Sanctuary for about 2.5 years. The Program and Operations Coordinator, which essentially means I do a little bit of everything. My background is in maritime archaeology. And that's kind of what I bring to the party here, but I'm also working on exhibits for this building, involved in creating this facility and doing some operational things as well. The goal of the exhibits at the Great Lakes Maritime Heritage Center is to service everyone, from researchers, from archaeologists to historians, to kids, to adults, to armchair sailors, you name it, we want to have something for them. Well, Science on a Sphere really launches us into the natural realm. And we do shipwrecks very well here, but the sanctuary obviously is an ecosystem, and the shipwrecks themselves were affected by weather. Many sank because of weather. So it kind of rounds out the picture for us. We can do geology, we can do weather, we can do all the things that kind of put the shipwrecks of Thunder Bay in context. And it's fascinating in and of itself. It's almost like a piece of abstract art. I mean, just the visual is compelling. And once people are drawn into the visual, now they start thinking about weather and patterns and the bigger picture of the Great Lakes. That's really important. And then they can come back and think about shipwrecks and how shipwrecks fit into the Great Lakes.
Here is our nearest planetary neighbor, Mars, as seen by a NASA satellite. Mars rotates on a tilted axis of about 25 degrees, meaning Mars has seasons, just like the Earth. Other similarities include land features such as canyons, mountains, and polar ice caps. If you've been to the Grand Canyon, you know that it is very deep. It is actually more than 1 mile deep and over 200 miles long. On Mars, notice the long gash in its southern hemisphere. That is the Mariner Valley. It is over 2,500 miles long and 5 miles deep, a canyon that would stretch across the United States. Now, look to the left of the Mariner Valley to see an example of a Mars mountain. That is Olympus Mons, an extinct volcano. It is estimated that Olympus Mons grew to well over 85,000 feet before it stopped erupting. By comparison, Earth's Mount Everest is around 29,000 feet, but it's still growing due to the push of plate tectonic activity. The recent exploration by the NASA Mars rovers seems to support the idea that there was once a great deal of water on the Martian surface. Scientists have long speculated that the lower elevation northern hemisphere once held vast oceans. At the poles, there are still ice caps consisting mainly of frozen water, but they are relatively small compared to the Earth's Antarctic ice cap. Here is the beautiful image of Earth called the Blue Marble by NASA. NASA assembled this image from a number of different satellites, to look like the Earth on a typical day. The vegetation detail comes from the MODIS sensor, and the clouds are a composite of 3 days visible cloud imagery taken in 2001. For most of us, this is probably the closest we'll ever get to being an astronaut in outer space, looking back at the Earth.
This now concludes our presentation of Science on a Sphere. You've just seen some sample data sets that demonstrate the potential of using Science on a Sphere for education and scientific discovery. NOAA is installing Science on a Sphere in museums. This museum program will provide better access to Earth science information for both school groups and the general public. Through such education and outreach efforts, NOAA hopes to inspire and help the public make better, more informed decisions about the health of the Earth's oceans and atmosphere.